Record to this. Good. Unfortunate disruption. Huh? I have to check with my internet provider what's going on. And I have two internet providers. Ah, I never had this problem with before. Okay, here we go. Gonna start sharing my screen. Go to the bottom. Mhm. Yep, in geometric optics, we usually want to determine the position of the light source, of the light source or the object. We also call it the object or the object. And that is a very straightforward geometrical approach to determine this position. Okay? Well, you already know how to determine the light ray that is reflected from a surface. You already know how to do that, right? And let's go back to my PowerPoint presentation. Go. Here you go. That's how we determine the reflected light ray. And that is, let me copy that one. Here you go, this one here. Copy it and paste it right in here. Here you go. The light ray coming from the source, incident in the planar mirror, and is being reflected at the same angle as the angle of incidence. So what else do you have to do, right? You have to draw this reflected light ray, and on the top of that, you also have to extend the reflected light ray, just like I extended here with this dashed line. Okay, and in order to determine the position of the image of the source, okay, we have to have a second light ray being incident in the mirror. And here you go. Here's the second light ray incident in the mirror. I'm gonna play the movie, right? Here you go. This one, incident light ray, reflected light ray, and the extension of the reflected light ray backwards. And I want to get this guy better. Like that. Yeah. Yeah. Uh, yeah, now I got it right. Good. In order to find out the position of the image of this light source, we are going to need a second incident light ray on the mirror. Here you go. Here's my second incident light ray, right? Next, we are going to draw. Oh, draw the reflected light ray. Okay, let me erase that for now. And then we draw this extension of the second reflected light ray. Note, see that the extension of this second reflected light ray coincides with the extension of the first reflected light ray. And that's exactly at this point where the image is seen to be formed. Okay? And it happens that for a planar mirror, the distance of the image to the reflecting surface is the same distance of the source or the object, right, to the planar surface. And consequently, the distance from S to S prime is going to be twice the distance of the source. Make sense? It's a very simple technique, right? Let's do that again. Here you go. First incident light ray, angle of incidence. First reflected light ray, that's the angle of reflection. We extend backwards, right? The reflected light ray. And then we need a second incident light ray. This incident light ray has a reflection. And we extend the second reflected light ray. The second reflected light ray intersects with the first reflected light ray. And that's going to be the position of the image of the source. And like I said before, the distance of the source to the surface of the planar mirror is equal to the distance of the image to the planar mirror as well. That's for a planar mirror. For other types of mirror, it's going to be different. You can repeat the same procedure for a third light ray if you want to, if you want to make sure everything is working, right? Here you go. Here is the third light ray in blue color, which is going to be reflected at the same angle of incidence. Another student joining. And we're going to have a third reflected light ray extended backwards, just like the other two. And if you did everything right, if you made the angle of incidence here of the light ray equal to the angle of reflection, whatever the point that this extension is going to coincide is going to be the same as before. That's a very simple geometrical technique that works very well. Let's write that down. So now let us find out the position of the image of the source, which for a planar mirror happens to be formed behind the mirror. Okay, step by step, right? You need only two incident light rays to determine this position. All right? Oh, here you go. 1, draw the reflecting surface. 2, Draw the point light source in front of the reflecting surface, step by step. 3, draw one possible light ray coming from the source S, right? Draw the point light source. Draw a point light source, right? A reflecting surface. Draw a reflecting surface. Draw a point light source in front of the reflecting surface. Draw one possible light ray coming from the light source S. 4, draw the reflecting light ray at an angle equal to the angle of incidence. 5, extend the reflecting, draw the reflected light ray, right? Draw reflecting surface, draw point light source. Coming from the light source, this is the incident light ray. Here you go. This is the incident light ray. Draw the reflected light ray at an angle equal to the angle of incidence. Don't forget, this angle is measured with respect to the direction that is normal to the reflecting surface. Extended the reflected light ray, extended direction of the direction of the reflected light ray behind the mirror. 6, repeat the steps 3, 4, and 5 for a different light ray incident in the mirror at a different for a second light ray, right? For a second light ray incident of the mirror at a different angle. 3, 4, and 5. The extended direction of the second light ray should intersect the extended direction of the first light ray. This point of intersection, this point of intersection is the position where the image of the source is formed. Okay? You can also repeat the steps 3, 4, and 5 for a third light ray. The intersection of the extended of this the extended light ray the extended reflection, right? The extended reflection of this third light ray should coincide with the previous intersection. Okay, and let's see, the extended direction of the second should intersect the extended direction of the first light ray. This point of intersection, S prime, okay, is the position where the image of the source is formed. So those are the steps. And we are going to elaborate on how this thing is done for a spherical mirror later on, okay? That's what we're going to do. But now let's take our break. It is 10:44. Okay, break. Any questions? 10:45, right? AM to 11 AM. Let's see if we have any questions. I don't see any questions here. And we have 11 students. Okay, so I see you in 15 minutes. Bye-bye. Back here. And there is a student that's trying to get in, right? It's taking some time for her to get in. Okay. Now, let's as of now, right? As of now, we showed how to determine the position of an image, the position of the image of a point source What if the source has a dimension instead, right? We will do for this case. We will now proceed to determine the position of an extended source, not a point source, right? A point source has no dimension whatsoever. And how do we do that? Here you go. We start again from scratch. Am I sharing the screen? Yes, I'm sharing. The mirror, right? And now we are going to come up with the axis of the mirror. And we are going to draw the extended source as though the extended source and the object as though it is an arrow. Okay, instead of a single point with no dimension whatsoever, now we have this object, it has a dimension. The distance of this object, we call it d naught. Let's see if I want to make sure that the book uses the same notation so you don't get confused, right? If necessary, I'll change my notation to to conform to the notation of the book. Let's go there. Launch. Reflection. Wavefront and rays. Okay. Reflection of light. Okay, the incident ray. We covered that. Here's the case of a surface that nice and planar. And here's the case of a surface that has all sorts of undulations, right? The same principle applies. Angle of incidence is equal to the angle of reflection. Formation of image by a plane mirror. That's what we're doing. Okay, and let's see what's the notation that object. Okay, D naught. Yeah, it's the same notation. The book is using the same notation as I am using. Here he drew a piece of the horse, right? One of the pieces of the chess. I'm drawing something much simpler that is just an arrow. Okay, so here you go, D naught. D naught is the distance of the object to the surface of the mirror. The first, we are going to use a light ray coming from the tip of the object. And this light ray is going to be parallel to the axis of the mirror. The angle of incidence in this case is 0 degrees. Okay? Consequently, the mirror is going to reflect back along the same path of the incident mirror, of the incident ray. One light ray from the tip. We have to have at least 2 light rays coming from the tip. Okay, so we're going to get the second light ray here. Incident at the intersection of the axis of the mirror with the mirror. And then this light ray is going to reflect just like that. Okay. This thing is not supposed to be here. Let's see. Yeah, let me take it out. We don't need that. And yep. Now, next, what do we do next? We extend the reflected light ray behind the mirror, just like we did before. And this one here, let's see how I'm gonna do that. I'm gonna do that dashed. Right, here you go. And second light ray, gonna be, let's see if I can do dashed as well. This one I can dash, the other one I believe I can't. If I dash this one, everything else is going to be dashed, right? But that's okay. First, let me copy and paste. And now I can dash it. Yeah. Here you go. Intersection of those two dashed rays is the point where the image of the object is formed. Object, I'm denoting that by the letter O. The image, I'm denoting it by the letter I. Let's see if the book does the same thing. It doesn't. Okay. The other end of the arrow is going to be formed right in here, right? Right below. And then you can do the same thing here. One point of the tip of the arrow, the other point is the beginning of the arrow, right? You can do the same thing that you did before. You know, a light ray that goes like that, right? And you're going to find out that the foot of the light ray is going to be exactly at this point as well. Okay? Let's see this. Okay, and you can find out because those triangles are similar. This distance di is going to be equal to the distance d naught. And then we can go ahead and write it down here. For an extended object, we replace the point light source with an upward arrow. Accordingly, the steps to determine the position of the image of the object are similar to that of a point source. One, right? I'm going to copy and paste what we had before. One, draw the reflecting surface. Draw the extended object as a narrow in front of the reflecting surface. Draw one possible light ray coming from the tip. A narrow, draw the extended object O, right? Draw one possible light ray coming from the tip of the object O. Draw a light ray, coming from the tip of the object O, parallel to the axis of the mirror, right? This is the incident light ray. And by the way, I have to draw one more thing here, right? Draw the axis of the mirror perpendicular to the reflecting surface. Draw an extended object, right? Now it's gotta be an axis, an extended object, an axis. Okay. The beginning of the arrow. The arrow should start at the axis of the mirror. This arrow, this object is said to be at a distance d naught of the mirror. Go. Here you go. Right here. Draw a light ray coming from the tip of the object O, parallel to the axis of the mirror. This is the incident light ray. The reflected light ray is reflected along the same direction of incidence, right? Because what? Because the angle of incidence is 0 degrees, right? Because the angle of incidence because the angle of incidence, because the angle of incidence of the tip of the arrow, of the tip of the arrow is 0 degrees, comma. The reflected light ray is reflected along the same direction of the incident ray. Draw okay, here you go. Let's not forget, right? Both angles of incidence and reflection are measured with respect to the normal of the mirror surface. Extend the direction of the first reflected light ray behind the mirror. Repeat steps. Let's see. 3, no. Repeat steps 4, 5, and 6. 4, 5, and 6. For a second light ray, incident at the point where the axis of the mirror intersects with the mirror. The extended direction of the second light ray behind should intersect the extended direction of the first light ray. This point of intersection S prime, let's see, I put S prime. Let's name it S prime. S prime. And this one here is point S, right? Is the position where the image of the source is formed. You can also repeat steps 4, 5, and 6. 4, 5, and 6 for a third light ray of the previous intersection. One more student trying to come in. Let's see. Let's see. Noemi was having a hard time to join in, right, Noemi? Looks like you managed to do that right now. So practice that until it becomes second nature to you. times that. So let's take a look what we have covered so far. Okay, here you go. Wavefront and light rays, reflection of light, formation of image by a planar mirror. Let's, here you go, right in here. Should be 25 wavefront and rays, reflection of light, formation of image by a plane mirror. We cover all of that. And now we're going to get into a more difficult topic, which uses the same principles we have been using, and is a different reflecting surface. It's a spherical mirror, not a plane mirror. Spherical mirrors. Okay, and here you go. That's what a spherical mirror looks like. You draw a spherical surface of radius r, right? You cut a section of this sphere, and you form the surface of a spherical mirror. There are techniques that allow you to do that. I used to build the spherical mirrors, by the way. But that's how you, geometrically, that's how you should envision this spherical mirror. It's a hubcap, right? From your car, from the tire of your car, the wheel of your car. And this hubcap has a radius of curvature r. Radius of curvature r. Let's see how light behaves, okay, through this mirror. You know, think about that. If we have a light ray passing through the center of curvature of this mirror, it's going to be incident at an angle of 90 degrees with respect to this tangent surface, okay? And because of that, the light is going to be reflected back towards the center of curvature, whether it is light ray, whether it's this other light ray. Can you picture that? That's one important characteristic of a light ray.
I have a question, Professor.
Yeah.
Is this, you know how you said it's similar to a hubcap? Would it be similar to like the lens in your glasses, like how it's like concave, or no?
Yes. This look at here. This surface here is concave, right?
Right, right, right.
Right. And the lenses of your glass we're going to cover later on in the next chapter. We
Oh,
can
okay.
have a surface that's either concave or convex. And
Okay, so excuse me. The spherical mirror that you're talking about, is it concave or convex?
yeah, this surface here is the concave surface, right?
Okay.
And
All
but
right.
you can also make this outside surface reflecting as well, and that would
Mm-hmm.
be a convex mirror. And we do have
Okay.
convex mirrors out there. Yeah, we can buy convex mirrors, right? Uh,
Yes.
in the drugstore, right?
Yes.
When I was your age, we couldn't buy
Mhm.
those things easily. We didn't have those things. Nowadays, we can buy those things so easily.
Right. Okay.
And
Thank you.
yeah, welcome. And we do have a picture of how a convex mirror forms images, right? Let's see okay, right here. That's the image. The being due to its curved surface, cloud gate sculpture. It looks like a convex mirror here. Okay, that's what it looks like. You can see that the buildings here are distorted, right? The image of the buildings are distorted. But it looks like this is a convex mirror. It doesn't say, right? The cloud gate sculpture created by artists is affectionately known as the being. due to its curved shape. Its highly polished stainless steel surface reflects the light around it, forming an image here of the buildings in Chicago skyline. The reflection of light and the properties of the image formed by this and other kinds of. Let's see. He doesn't say, but most likely is a convex mirror. Is not a glass, right? It's a stainless steel surface that highly polished cloud gate structure sculpture. Let's see if we have some more something more about this sculpture. About this page, VPN. Let me turn off my VPN. Ah. No, it's not what I want. Cloud Gate, Cloud Gate, Chicago. Let's see here, Cloud Gate, the Bean Hotels. No, I don't want that. I want something else. Oh, okay. Yeah, it is a convex surface. Okay, you can see the buildings being reflected by this convex surface, and this convex surface acts like a convex mirror. Highly polished stainless steel surface. It's not a concave, it's a convex in this one. So we're going to start covering the concave mirror. Here you go. That's how we represent a concave mirror. A flat surface with those borders here indicating that the surface is actually a concave surface, right? Even though I drew a flat surface here, in reality, this borders here means that the mirror is concave. Next, we do the same thing that we do before. We draw the axis of the mirror, and I want to extend it even further. Okay, I marked the point of curvature, the center of curvature. Letter C. This is the axis of the mirror. Let's see here. What you have to know? You have to know how the light behaves with respect to a concave mirror. The first light ray that you have to memorize is that one that passed through the center of curvature. Remember that? If you have a light ray passing through the center of curvature, it's going to reflect towards itself. Let's see if I have it here. Yeah, okay. And you saw that before, right? So, oh yeah, here you go. That's not the. Here you go. In the next drawing, I drew an actual spherical surface, right? It's a more realistic one. And that's the diameter of the mirror, diameter D. Okay, when you have a light ray that's parallel to the axis of the mirror, okay, like this one here, here's a light ray parallel to the axis of the mirror. At this point, it's going to be reflected with the same angle, right? Angle of incidence is equal to the angle of reflection. And that's the direction normal to the spherical surface of the mirror. This light ray that follows parallel to the axis of the mirror is reflected at a point here, this point here, as a name, is an important point. We call it the focal point. Okay? And this focal point, whenever the diameter of the mirror is much smaller than the radius of curvature of the mirror, right? C to C prime is equal to R, the radius of curvature of the mirror. then the light will intersect the axis at half the distance. That would be the focal point. Okay, so let's write down what we need to know. Spherical mirrors. Spherical mirrors. We will now study two different spherical mirrors. The concave mirror, and the convex mirror. Okay. Start with the concave mirrors. Concave mirrors. I'm going to draw a concave mirrors are represented. Let's see here. A simple representation of the concave mirror is this one here, with the axis of the mirror. Snipping tool. There you go. Simple representation of the concave mirror, of a concave mirror. Concave mirror. Okay. And then I'm gonna paste here a more realistic representation of concave mirror. There you go. That's the axis. I want the oops. I don't want that. I don't need that. I'll keep it there. Right here. A more realistic representation of a concave mirror. A more realistic drawing, right? Of a concave mirror. Concave spherical mirror. With drawn with its axis. So going back here, what I want to do, you go, that's one. Let's see, I'm going to do the following, step by step, right? Oops, that's not what I want. I want like that. Like here. Oops. No, that's the radius. That's the center of curvature. C is the center of curvature of the mirror. C prime is the point of intersection of the axis of the mirror with the surface of the mirror. Okay, I can go ahead. Let's see, I want an arrow here. This one? Yep. Here you go. That's the radius of curvature of the mirror. CC prime is what I called before R, right? CC prime is equal to R. R is equal to CC prime. Oh. What I want to do, I want to put this guy out here. And I put this R back right here. Okay. But this mirror also has a diameter. And that's what the diameter is. Here you go. Now, light rays that pass through the center of curvature of the mirror. Okay, there you go. I don't need that anymore, right? Are reflected back on itself. Oh, wait a minute, what's going on here? Here you go. Light ray. I want this one here. Let's see how I'm going to do that. Like that. The incident light ray and the reflected light ray. Any light ray that passes through the center of curvature is going to be reflected on itself. Going to draw it and let's get this thing grouped. Yep. And then I'm going to rotate it to show another light ray that passes through the center of curvature. All right. Another, and then you have a bunch of light rays that pass through the center of curvature. Let's write down what we have been doing here. Another student, let's get, Noemi is having a problem, huh? Okay. So drawing a concave spherical mirror. One. Draw a concave spherical mirrors. Let's see. Concave spherical mirrors. Concave spherical mirrors. Draw concave mirror. 2. Draw an axis of the mirror passing through its center and normal to the reflecting surface. Okay. Draw the center of curvature of the mirror. C. The center of curvature of the mirror is just the center, okay? The center of curvature of the mirror is just this, it's the center. The center of curvature of the mirror is just the center of the spherical surface. Noemi is having a problem. Let's see. Let's see if she joined us now. Can you hear me, Noemi? Huh. Oh, yeah, okay. Looks like you managed to sign in now, right, Noemi? So here you go. Draw the center of curvature of the mirror. See? Here you go. Here's the center of curvature, right? The point, uh, the point where we call, it's not the axis of the mirror, it's actually the principal axis of the mirror, right? Where the principal axis of the mirror intersects the mirror surface is point C prime. C, the distance C prime is equal to the radius of curvature of the mirror, radius of curvature R of the mirror. That is C prime. Let's see. Yeah, here you go. Right here. Do I need more than that? Let's see. Okay, here you go. Any light ray passing through the center of curvature reflects back towards itself. We will need the following light rays, okay? We will. There are some important light rays that you have to memorize. One, light rays that passes through the center of curvature of the mirror. See, reflects on itself, right? There are some important light rays that you have to memorize that pass, reflect on themselves, right? Reflect on themselves like that. And here's the illustration. Why reflect again? Why does it reflect on themselves? That's because any light ray that passes through the center of curvature is going to be normal to the surface. Since it's normal to the surface, its angle of incidence is 0 degrees. Angle of reflection must be equal to the angle of incidence. Consequently, the angle of reflection is going to be 0 degrees as well. So the light ray is going to be reflected upon itself. Another important light ray are light rays that are parallel to the principal axis of the mirror. Okay, let me rename it. I just put mirror of the axis of the mirror is the principal axis of the mirror. Principal axis of the mirror. Principal. Go. Here you go. Light rays. Let's write it down. You have to memorize. Light rays that are parallel to the principal axis of the mirror. Principal axis of the mirror are reflected between points C and C prime. And C prime. Special case. Special case, which by the way is very important. It's a special case, but it's very important. Very important. Very important special case. Very important special case. Case. If the diameter of the mirror D is much less than R, than the radius of curvature, right? By much less, you know what we mean? We mean that D must be less, this one here, than 10 times R divided by 10. If the diameter of the mirror is much less than its radius of curvature, or, okay, to say that the diameter is much less than the radius of curvature means that the diameter should be at least less than 1/10 of the radius of the mirror. Then the light ray passes the reflected light ray. The reflected light ray passes. It's possible to prove that too. Okay, mathematics. We're not going to do that here. Passes through the focal point of the mirror, focal point F of the mirror, which is at a distance where, let's see, of the mirror, where you go. Whereas SC prime is equal to half the radius of curvature of the mirror. Can you remember that? Or even better, half C prime is going to be equal to half to FC, but then you go half R. Okay? You go, I didn't put F there, right? Let's see, here you go. I put F here. Focal point and here you go. Focal point. Next, here you go. CC prime divided by 2 is also called the focal distance of the mirror. Okay. This distance is also called the focal distance of the mirror, focal distance, lowercase f, of the mirror. Okay. So those are two very important. Let's see if we have another one. Oh yeah, we have another one. Another important light ray. Let's see if I have a drawing here of this other important light ray. Principal axis of the mirror, right? Principal axis of the mirror. light ray parallel to the principal axis of the mirror passes through the focal point. Another different light ray parallel to the principal axis of the mirror still passes through the focal point. But you must have this condition here, right? The diameter must be much, strictly speaking, it does not always apply. It applies only if this condition holds. What else can we say? Light rays that passes through the focal point, another light ray, is reflected parallel to the axis of the mirror, right? So it's the opposite to the other one that you saw. The other one is the inverse, right? Light rays that are incident parallel to the axis pass through the focal point. And light rays that are incident through the focal point are reflected parallel to the principal axis of the mirror. Three important light rays that you have to remember. Here you go. Another one, another drawing. And let's get this one here. Third light ray. Light rays that pass through the focal point F are reflected parallel to the principal axis of the mirror. And one final light ray that I want you to memorize, only four. In general, you're going to need only two of those light rays to find out the position of the image, okay? Okay, another a light ray that is incident at the very center of the mirror is reflected back at the same angle with respect to the principal axis, okay? This angle here is equal to this angle here. Don't forget principal axis. Axis of the mirror. Four important light rays. And here are several examples of different light rays incident at the center of the mirror. There are four, let's put here, there are four important light rays that you have to remember, to memorize. Light rays that pass through the center of curvature reflect on it. Light rays reflect on themselves. Light rays that are parallel to the principal axis of the mirror are reflected between point C and C prime. There is a very important special case for this light ray. If the diameter of the mirror is much less than its radius of curvature, right? Then the reflected light ray passes through the focal point F of the mirror, whereas the focal point is at a distance equal to half the radius of curvature of the mirror. Light rays that pass through the focal point F are reflected parallel to the principal axis, the inverse of the previous case. The inverse of the previous case. Okay, the same, and by the way, the same conditions, the same condition holds, or D must be much less than the radius of curvature of the mirror. And finally, light rays that are incident at the center of the mirror, comma, are reflected at the same angle with respect, right? Whereas the angle at the same angle, whereas the angle go with respect to the principal axis of the mirror. That's 10:55, right? 11:55. Let's have our break. And when we come back, we are going to do some examples of how we use this information, okay? Break 11:55 a.m. to 12:10 p.m. Okay, so I see you in 15 minutes. We I am back. Okay, so now we are going to apply all this knowledge that we discussed to determine the image, the position of the image of an object that is reflected by a concave mirror. We start with the concave mirror, right? We draw the principal axis of the mirror. Let's extend all the way down to the back of the mirror. Let's see here, a little bit down, like that. Now let's get this copied and pasted here. Let's see. Like that, good. We draw the center of curvature of the mirror and the focal point of the mirror. We draw the point C prime, that is the intersection between the principal axis of the mirror and the mirror itself. We draw the object. This object is now being drawn past the center of curvature. Then we are going to do some other special cases, okay? That's one case that we're going to do. Then we are going to do the case in which the object sits exactly at C, sits between the focal point and the center of curvature, and between the focal point and the mirror. We're going to do 1, 2, 3, 4, let's see, 1, 2, 3, 4, and 5 cases. At C, at F, and between F and C prime. And I'm gonna do something else too. I'm going to mark this point C prime right in here. Okay, so don't forget we are doing the case in which the diameter of the mirror is much less than the radius of curvature of the mirror. The distance between, oh, here you go. Here's my first light ray. Light ray parallel to the axis of the mirror. Incident at the surface of the mirror is reflected towards the focal point. Okay? One light ray. We need only 2 light rays to find out the position of the image. That's all. The second light ray that I'm going to choose is the one that passes through the focal point. But I could have chosen another one, okay, if I wanted. And this light ray is reflected parallel to the principal axis of the mirror. And now we have the intersection between those 2 light rays. But like I said, if you want to make sure, like me, right, that they are doing everything right, you can come up with a third light ray, but it's not necessary. The third light ray is the one that passes through the center of curvature. And the light ray is reflected back towards the center of curvature. If you do everything right, this light ray will intersect at the same point that the other two light rays intersected. And here you go, point of intersection of 3 light rays. Okay. We could draw the 4th light ray, right? The 4th light ray that goes exactly towards the center, the intersection of the mirror and the principal axis. And the 4 light ray would be reflected towards the same point. Here you go. Here's the image in red color. Let's zoom in. Okay, that's the image where it is formed. This image is formed between, in this case, between the focal point and the center of curvature. And notice that the image is inverted. Notice that the image is inverted. Okay. This is the type of image that we can project into a screen, onto a screen. Let me zoom out. D naught is the distance of the object to the mirror, and di is the distance of the image to the mirror. View, let me see, zoom. I want to zoom out. Too small. Let's try 150%. Yeah, 150. Can we do better than that? Well, let's leave it this way. Next, okay, that's one of them. Now we're going to move the object closer to the mirror. Okay, again, concave mirror, principal axis of the mirror, center of curvature, focal point, C prime, the point where the principal axis intersect with the mirror. Object, oh, the object now is exactly at the center of curvature. Okay, here you go. Light ray parallel to the axis, principal axis, is reflected towards the focal point. Another light ray passing through the focal point is reflected parallel to the axis. Okay. And here we have the image formation. Again, it is inverted. In the previous image that you saw, the images were also inverted, but it was smaller than the object. We can prove that mathematically, okay? We can prove that mathematically. Here in this case, because the object is sitting exactly at the center of curvature, the image is going to have the same size as that of the object. Next, oh, that's the 3rd light ray. That's the 3rd light ray that passes through the center of curvature, okay? It's just in the vertical direction, because the object is sitting exactly at the center of curvature. So the light ray that passes through the center of curvature is going to be pointing downwards. And here is the 4th light ray at this, that's the incident at the center of the mirror. The image is formed exactly at the center of curvature. What next? Let's see. We did that, right? Why is that? Okay. Next. Okay, let's document here. We are going to cover the following cases. For the object position. 1 after past the center of curvature of the mirror. You know what? Let's put it instead. I didn't cover that, but we're going to put another one. 1, the object is positioned is infinitely distant. Okay, here you go. That's a special case, distant from the mirror. I didn't illustrate that, but this is an important special case. Between the center of curvature, past the center of curvature, right? Here you go, between that's the one I illustrated, the center of curvature, and at a point, infinitely distant from the mirror, like that. 3, for the we're going to cover the following case of the object position. Okay, following case: object positioned at infinitely distance from the mirror, at an infinitely distance from the mirror, between the center of curvature and another point, past the center of curvature. Let's put past the center of curvature. Let's not complicate the center of curvature of the mirror. The center of curvature of the mirror. What else? Between the center of curvature and the curvature and the focal point of the mirror, right? At the focal point of the mirror, between the mirror and the focal point. Six different cases, right? I did this one, and I did this one. Position at. I did those two. Now let's take a look at this, the next one. Center of curvature, focal point, object. Wait a minute, I don't want that. Why am I repeating that? Let's move forward. Let's see here. Okay, center of curvature. Okay, now we are going to get the object between the center of curvature. Oh, wait a minute. Now, let's see. I'll have to do that from scratch. Let's see here. This one is repeated. Let's clean up this presentation, right? So I don't have to keep on showing that. That's first case. Here you go. Yeah, okay, first case. First case, no, second case, right? That's the third case. Okay, now I don't need that. I don't need that because we're just repeating what we did before, right? Don't need that, don't need that. Let's see, this one, do I need this one? I don't need that either. Okay, I will need those, but I don't need this, 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 this. I don't need this one. Okay, here you go. The next one is, oops. Now I gotta put my object between the center of curvature. Hey, come on, man. Oops. Yeah. Oops. Here we go. This one. This object now is gonna move here. I don't need. Here you go. Okay. Okay. So first light ray, parallel to the axis. Let me use, yeah, here you go. This one, right? Parallel to the axis. Here you go. Yeah. Nope, not this one. The other one. Here you go. Now we got it. Here you go. That's what I want. First light ray incident. Then we have light ray reflected, which now you can choose whatever light ray you want. You can choose a light ray that passes through the center of curvature and reflect back, okay? Or you can choose a light ray that passes through the focal point and reflects parallel. Or you can choose another light ray that goes up to the center, right, and reflect here. I prefer the light ray that passes through the focal point. Here you go. Why the thing is here? Ah, yeah, I know why. I forgot to reposition it. Let's reposition it. Here you go. Focal point. No, this one should be before. Okay, here you go. Now it's go. Here you go. Mirror, principal axis, percent. Nope. Zoom. Okay. Let's try 150. Good, larger. Can I do 200? Yeah, I can do 200. Good. Now it's better. Here, axis, center of curvature, focal point, object, right? Okay, what I want to do like that. I'm playing the movie here. What? Okay. Why is it doing that? Oh, gosh. Good. Yeah. Yeah, I don't want this one. Okay, here you go. Okay, focal point. Now we put the object. Light ray, parallel to the axis, passing through the focal point. Next is a light ray incident that passes through the focal point, like that. Here you go. Right? Nice. Here you go. Like that. And reflected parallel to the okay, reflected parallel to the axis. We can come up with this other light ray here. Let me show you which other one I can show you. We can have, we don't need it, but it's always good to know, right? A light ray that passes through the tip of the arrow and the center of curvature. Tip of the arrow and the center of curvature. It is going to be reflected into itself. Let's see if I can get it right. Okay, we can, it is as though as this mirror is extended all the way down here, okay? Let's see if I got it. That would be my third light ray. And if I do everything right, this arrow is going to intersect right in here. Supposed to intersect right in here. That's the surface of the mirror that I extended all the way down there. And we must have a double arrow here. Yeah, double arrow. Like that. Oops. All right, that's close enough. We can. Maybe this guy should raise a little bit, right? Like that. The other one is that one that reflects here and should intersect here as well. And then what we get? We get an image that's going to be right in here, but it's going to be downwards, upside down, just like before. Format shape, you go. Like that. And because it is an image, I'm going to draw it dashed. Like that. Like that. Yeah, here you go. And I'm going to put it a different color, like I did before, image. One more. One more. One, two, two, three, four. Yeah, okay. Okay, now the object is going to fall right in here at the focal point. right here, the focal point. That's an interesting case as well. We have 15 more minutes to go. I'm going to take advantage of the other light rays that we have dealt with, right? Here you go. This one. This one. Okay. Light ray parallel to the axis, reflected towards the focal point. Parallel to the axis, reflected towards the focal point. Another light ray. Which one? Which one can light ray? That is, we can do this one right in here. The one that passes through the center of curvature, right? Light ray that passes through the center of curvature is reflected back. Note, see that this light ray is going to be parallel to this other light ray. And then we are going to have another, we can also have another light ray that is going to be incident right in here. And it is also going to be reflected parallel to the axis, parallel to the other two light rays. There will be no image formation whatsoever in this case. In this case, there will be no image formation. And the final one, okay, here you go. CF. Now the object is going to be between the mirror and the focal point. Just like before, light ray parallel to the axis is going to reflect through the focal point. Another light ray that passes through the center of curvature should look like that. Reflects back in the same direction. Let me clean up this guy here so you don't get confused, right? Here you go. Let's see, I missed, yeah. First light ray, we don't need this one, yeah. First light ray, second light ray passing through the center of curvature. Notice that those two light rays, they are diverging from each other. They are not going to intersect each other, okay? Let's get a third light ray. 10 more minutes to go. Let's get this light ray here. Okay. And this light ray must also diverge from the other one. And how do we find out an image for this object? Because they are diverging from each other on the left side, notice that they're converging on the right side. This is going to be a different type of image, by the way. Okay, it's an image that cannot be projected onto a screen. Instead, it's an image that's going to be formed behind the mirror. This type of image has an important name. Go. I'm gonna dash this one so you know it is like that. Another one. You go. They're going to intersect behind the mirror. I'm gonna tell you exactly what type of image this one is. Dash. I'm gonna dash this one as well. This one, okay? And if I do everything right, all those three light rays are going to intersect at the same point. Yeah, it looks like I did it. Intersection. Yeah, more or less, right? And look what happens. Here you go. I'm going to extend this axis. It's an image that's formed behind the mirror. And it's a larger image. Okay? This one right here. Because the image is formed behind the mirror, we call that a virtual image. This case here is 9 more minutes to go. Virtual image. The other case in which no image is formed, the one that there is no intersection between the light rays, like this one here, we call it improper image. Proper image. The other one in which the image is formed in front of the mirror, we call it real image. If one is virtual, the other is going to be real. Real image. All the others are going to be real image as well. This one is also a real image. This one is also a real image. Okay. Now, the difference is that this is a real image, but it's also smaller, right? It's smaller than the object. Real image. Smaller. Smaller than the object. Object. I'm going to copy that. Real image. Same size. Same size as the object. And then the other one, the other real image, larger than the object. That's the type of image that we have in the movie theater, okay? But don't forget, the image is inverted, okay? So in order to reinvert the image, we have to have an object that's upside down. What about that's the improper image? And that is the virtual image that's larger than object. And if you want to, 5 more minutes to go, if you want to dive deep into that, instead of doing all this work, but it's important to do this work because if you do that on your own, right, you're going to understand better. But if you forget everything that I mentioned here, you can go in the internet and look for simulation of concave mirrors. Concave mirror. There are all sorts of simulations out there that are very good. Let's take a look. There, there is the fat simulation. Let's take a look at this one here. Yeah, here you go. This one is a good one. Everything that I did is right in here. Everything that I did is right in here. Here you go. I start with the object very far away from the mirror, right? And here's the image upside down. Let me see if I can move my now I cannot move it, unfortunately. Okay, I cannot move. Okay, so notice that as the object approaches the mirror, the image is formed further and further away from the object. At the very center of curvature, the image is upside down and has the same size. Okay, as the object approaches the mirror, the image is formed further and further away. Like I said before, this is the case of your image projected in a movie, in the screen of the movie, okay? You have the object very close to the focal point of the machine, of the lens, and here's the projection in the screen. The projection in the screen is larger than the object. As the object approaches the focal point, the image grows larger and larger until it comes to the point. Not only grows larger and larger, but it positions further and further away from the mirror. At the focal point, we have that improper image. No intersection between the light rays. There is no image formation whatsoever. And when the object goes past the focal point, the image becomes virtual, right here, virtual image. And the image is larger than the object. See that? Here you go. Here's the image right here. Let me get this. Simulation here, important simulation. 2 more minutes to go. Okay. And as the object approaches the mirror surface, the improper image decreases in size, right? One last thing before we go home, right? Everything that you see here can be modeled as a single equation. Okay. The equation, everything that we did here, everything we did, I didn't document, unfortunately, right? We did here can be modeled with a single mathematical equation. And the mathematical equation is very easy to memorize, which is very easy to memorize. Here you go. Let's get my equations in place here. Insert equation right here. So it goes like that. The inverse of the focal distance is equal to the inverse of the distance of the object plus the inverse of the distance of the image. Everything that we did here can be wrapped up in this single equation, okay? And we'll be working on this equation, which applies not just for the concave mirror, but also for the convex mirror and for the concave and convex lenses, okay? We can stop right now. It is 12:50. And if you don't have any questions, I'll see you next week, and I'll be here 1 more hour for my office hours. Okay? See you next week.
Thank you.
Welcome.